Now that we've looked at the graphs of trig functions and some of the properties of those functions, we're going to return to calculus and actually look at the derivatives of these trig functions. There are lots of ways to derive the derivatives of sine and cosine. Take a look on the web if you're interested in various options out there. We're going to start with a graphical approach though. Here is the graph of sine of x. It goes up to 1, goes down to -1, has its zeros at 0, pi, 2 pi, and so on. Now, remembering what we mean by the relationship between the graph of f of x and its derivative, if we take a look at this graph and look at slopes, we're going to see values on this function here. What do I mean by that? We take a point, we see a slope of 0. That means we're going to get a value, a dot on this graph at height 0. Likewise, at this point here, the slope is 0. We're going to get a dot at value 0. And same thing here, peak and valley, slope of 0 means a value f prime of 0. Slope of 0, f prime of 0. What can we say in between those? Here we can say that f of x is increasing. The corresponding interpretation, or the way we visualize that on the derivative graph, well, if our function is increasing, our derivative is positive. And we can get even a little more specific with that. This graph is actually to scale, and 1.7 here is a bit longer than 1, a bit further than 1, 1.6-ish. And the slope here is actually exactly 1. This is another reason why we use radians in calculus class when we talk about trig functions. If we scale the axes here, so one cycle takes 2 pi, then this slope is exactly 1. And then we see the slopes get lower and lower and lower and hit 0. So the values of the derivative get smaller and smaller until they hit 0. And likewise here, the values are 0, then they get bigger and bigger and bigger. 0, bigger and bigger and bigger. Oh, we might see a nice arch like this. On the next interval, we see that our function is decreasing. And the translation about the derivative then, we say the derivative is negative on this next interval. Well, not too surprisingly, in the middle here we expect to see a slope of the same as this but negative, so we see a slope of -1. And hey, keep repeating those patterns and pretty soon you start seeing a graph that looks an awful lot like, starts at its peak, goes down, has an amplitude of 1, period of 2 pi. We have the derivative of sine of x is cos of x. This is not a proof by any stretch of the imagination, but it ties in graphically, or builds a relationship graphically between those two functions. So it's certainly plausible that the derivative of sine of x is cos of x, and that is in fact true. Let's immortalize that in a theorem box just to get that down for posterity. And then we'll take a look at the derivatives of all the other trig functions that are commonly used. Here is this table of other derivatives. The one gotcha one that is most commonly used is the derivative of cos is negative sign. So just be aware that that negative creeps in. The derivative of tan is secant squared. You can actually derive this and all the other rules from basic trig identities and the derivative rules. If you take the derivative of tan, that's the same as the derivative of sine of x over cos of x, and if you do some work, you can get back to secant of x, just remembering that secant of x is 1 over cos, so secant squared of x is 1 over cos squared. So this rule, if you don't remember it off the top of your head, you can derive it in about 3 steps using the quotient rule and the definition of tan. The same is true for these other 3 derivatives. It's up to you how you want to remember them. The one pattern that does stick with me is that if there's a c in the function itself, cosecant, cos, or cotangent, those derivatives all have negatives in them. Sine, tan, and secant all have positive derivatives. There's some other structure about secant squared versus cosecant squared, that kind of thing. Whatever mnemonic works for you. The main ones, of course, though, are the derivative of sine is cos, and the derivative of cos is negative sine. Let's do a quick proof of the secant rule just to see how that plays out. The derivative of the secant of x is more easily stated as the derivative of 1 over cos of x, because we know the rule for cos of x, and that is better stated as the derivative of cos of x all to the power -1. That'll be another way to write the same thing. And now we have a classic chain rule application where we have the derivative of something to the -1, and then we get the same thing inside, cos of x to the -2, and then we take the derivative of the inside, and the derivative of cosine is negative sine of x. That doesn't get us all the way to the end, but we can see some cancellations. We have a negative and a negative, so we're going to get a positive overall. Cosine to the -2 is 1 over cosine squared of x, and then we have a sine of x left over. That's a perfectly acceptable form of the derivative. Historically, though, we tend to put it in this form here, and it's not too hard to do. All we do is take this cosine of x all squared and break it into 1 cos of x in one term times the sine of x with the other cos of x. So we split this cos squared into 1 cos on the left, 1 cos on the right, and lo and behold, sine over cos is what we define as tan, and 1 over cos is where we started all this with secant. So the derivative of secant x is secant x times tan of x. As a quick practice challenge, take a look at this function here and see, using the derivative rules for trig functions now and the chain rule, can you identify the derivative here in the list? I'll pause for a second, then we'll come back. All right, the derivative of 4 plus 6 cosine of pi x squared plus 1 is going to be derivative of a constant by itself is 0. The 6 is a multiplier, so it stays around. The derivative of cos anything from the chain rule is going to be negative sine of the same thing. And then we take the derivative of the inside and multiply by that. So we're going to have pi times 2x. All of that together should look like one of the expressions we have here. We've got -6 sine times 2 pi x. That leaves us with C being the correct answer. We could tidy up a bit more if we wanted to, but here is just enough to get the derivative value as a function.